Who are you and what do we need to know?
My name is William Haseltine. I'm a scientist. I was trained by 4 Nobel Prize winning scientists in the field of biomedicine. I've had a career dedicated primarily to helping people stay healthy, to avoid disease. I did that first by doing fundamental research on cancer. When HIV, AIDS came along, that was the last, but this great pandemic, so far it's killed about 34 million people and still kills about 1 million a year. Problems in hand, but not yet solved. And then I went on to found a number of biotech companies that brought 7 different drugs for different diseases to the market. So I've taken all the way from discovering new techniques to find drugs all the way to drug approval. For the last 15 or more years, I've been working on health policy. But the thread that unites all of that is trying to understand how to keep people healthy. What can we do as scientists, as citizens, to help everybody in the world enjoy the best of health?
You recently wrote, in fact, you're a prolific writer. You've written 11 books. You write regularly for Forbes, and you've recently written an article for Scientific American, the subject of which was how COVID-19 has changed science. Could you talk to us about that, please?
Well, thank you for mentioning my books. It's a lot of fun for me to help communicate ideas about science and health to people, not only in this country, but around the world. But in one respect, COVID has been a great gift to the scientific world because it's allowed us to do something we'd always wanted to do, which is seamless communication. One idea that people have about scientists is we're beavering away in secret in our labs. Well, that's true, but it's true only for a very short time, because in the past, the way you got credit for what you did is letting everybody else know you did it first. If you do it second, it doesn't count. So you do it secretly, and then you let everybody know right away. And that's gives the idea that things are secret, but it's not really. Science is a cooperative enterprise. What COVID has done is enormously enhanced the cooperativity of science. I'll just give you a couple of examples. One of them is publication. It used to be you submit a paper to a journal, and you were obligated, if they were to publish it, to keep it totally quiet until they publish it anywhere from 3 to 9 months later. That's a long gap. COVID has now allowed us to publish our research instantly. The moment we've got the result, we can post the paper before it's reviewed. Eventually, it does get into the journal, but that's a big change. Let me give you how big a change. When the Chinese lab first determined the sequence of the COVID virus, it was a week before that was widely known around the world. And over a weekend, that information was used to make what turns out to be the Moderna vaccine by a scientist in the United States. Well, that wouldn't have happened without instant communication. And that's happening all the time. Another good example is something I'm part of as an honorary member and pleased to be part of it, called mass CPR. I was a professor at Harvard for 20 years. And I can tell you it's a very insular community, or has been, where Harvard doesn't really speak to Tufts, doesn't speak to Northeastern, doesn't speak to the University of Massachusetts, et cetera. This event has coalesced that entire community into something called mass CPR. It's organized by some of my former students, I'm happy to say. And what's really great about that is the entire community works together. And every other week, we have a meeting where 6 scientists present about 5 minutes each, or 5 minutes, 5 scientists present 6 minutes each, their latest research that's unpublished. And it's fostered enormous collaboration. That's something that we can take into the future. We can take both a rapid publication, and it hasn't diminished scientific reputation. People are still known for their outstanding work. It's just that other people get to stand on their shoulders and see farther, quicker. And it's created institutional, not just cooperation within a place like Boston, but around the world. There's cooperation, which I've never seen before, which is means science can proceed much more rapidly. That's a gift to humanity that I think it will keep on giving.
Can we go back to the scientific challenges before we go on to talk more about how important cooperation, collaboration has been during the process of tackling this terrible disease? Can you talk to us about the importance of mRNA and the other technologies that have, and discoveries that have become absolutely critical to creating vaccines to tackle SARS-CoV-2?
Well, vaccines are one of our older technologies. Actually, when you trace it all the way back, it goes way back to China about 1400 years ago, where people would take the scabs of smallpox and grind it up. It was then used in the Middle East. And of course, we know that was one of the first vaccines where the name comes from. Vaca, cow, vaccine for smallpox. And we know the stories of Jenner. But it's been a continual upward progress. After that, people have learned to attenuate viruses, to make them weaker. Yellow fever during the Spanish-American War. At least that's what we call it, the Spanish-American War. They might call it something else. But that was a huge step forward. In my own life, polio vaccines. I knew Jonas Salk. I actually got to work in the lab, actually had the space where Sabin isolated the polio virus, and that made a huge advance. That was taking the virus growing up and killing it. Those are all techniques that work. And then I've been witness and helped participate in the revolution to use purified proteins, recombinant DNA technology. Actually, my first company was creating a cat vaccine to a retrovirus, and it's used very similar to some of the techniques that are using today. That was in 1983, 84. Very similar to the techniques that are used to make some of the vaccines today. We, in fact, invented what's called the adjuvant. You use an active agent, and then you stimulate the immune system by putting something into you that irritates you. That's why vaccines can irritate your arm. That's positive. You want your body to say, hey, something's here that shouldn't be here. Let me recognize it as foreign. That's the adjuvant. So we did a peptide, we did a adjuvant, and it's still used for protecting cats from viruses. So what is the mRNA and how does that fit into it? Well, it was recognized that you might be able to do things a lot faster if you could just simply chemically synthesize your vaccine active entity, and you could do it really quickly in a day or two, and then begin to test the vaccine right away. And you could respond to changes in the virus very quickly. And a number of groups, including the Gates Foundation, put a lot of effort behind that. The NIH put a lot of its efforts behind it. And when COVID came along, that's exactly what they did. This was about maybe the 7th or 8th time they tried to make a vaccine that worked. It turns out it was the right technology for the right virus. It turns out that the outside of the virus, which is most important to be recognized by the immune system, just likes to fold up all by itself. You don't have to do anything. It's like magic. It's like you wanted to make an origami phoenix and you looked at the paper and it folded up. And there you had what you wanted. This thing loves to form in the right structure without something called cysteine bonds. You don't have to worry about that. And that means when you make the protein from the messenger RNA, which Moderna and Pfizer have done, and now a couple of other companies are doing, you put it into the body as messenger RNA in a little lipid package, gets into the cells, the protein gets made, and the immune system sees it, and it's great. It's like one of the best vaccines we've ever seen in terms of 95% effectiveness and pretty high titers. May not last forever, but it's the best thing we've got right now. And it's been fast, really fast. That also helped because the entire government got behind it and used the processes, the whole machinery set up to respond to bioterror, to respond to this by allowing very rapid development to take place. We had greased those skids following the anthrax attacks and other concerns over bioterrorism, and we used them to great effect. And the mRNA technology has been good for that. How well it's going to be for other diseases remains to be seen.
And Johnson & Johnson and AstraZeneca use a vector technology. Could you talk of that a little, please?
Right. Well, a whole nother way to do vaccines is to introduce them into cells with a virus. Viruses naturally get into your cells. So you create a virus that only has a chance to go in once and can't spread around. And that's the adenovirus technology. It's widely used for gene therapy to get viruses into our nervous tissue. There's a great new experiment that was just done to put a new photoreceptor There's somebody whose photoreceptors had blinded him. 40 years later, when those genes end up and you put special goggles on, that man can see some things. He can he can see a crosswalk. He can count the number of bars in the crosswalk. He hadn't been able to see for 40 years. That's the adenovirus driving a gene into a useful cell. Well, the adenovirus can drive genes that can make the proteins of the virus into the appropriate cells, and it does so. And when it does it, it makes the body recognizes it's foreign, makes an immune reaction. Sputnik, the Russian vaccine, uses that. The J&J vaccine uses the adenovirus, and so does the AstraZeneca. It turns out it's not as effective as the mRNA technologies. For some reason, you don't make the same high level of antibodies. And that's a problem when you come to treating or trying to prevent some of the variants. For example, the efficacy of the Pfizer and Moderna vaccines is better than that of the adenovirus for seeing these variants. That's just because it makes more of the antibodies probably. But there are good technologies.
Can you take us through, please, the chronology of how collaboration has worked in this case? For example, a precedent was set by the researchers in China. Then another researcher in Australia shared the findings on Twitter, right, and so on. And we then arrived at a system that institutions have adopted. So it was really driven by humanness, motivation for the greater good.
That's true. I think the timeline for the development of not just the RNA vaccines, all of the generations of vaccines has been extraordinary. And no matter where you look, it's been much more rapid than for any other vaccine in history. And let's just take you through what you described as the Moderna, the vaccine. The Chinese group isolated the virus, determined its nucleic acid sequence, sent that to researchers in Australia, which then made it public. And within days, literally days, the messenger RNA vaccines were initiated. The first they were constructed. The same thing happened with the adenovirus. Because all you need is a sequence. You know, I realized I was one of the first people, in fact, probably the first group to sequence the AIDS virus. And I realized that once you have the sequence of the virus, you don't need to know much else to get drugs and vaccines going. That's the power of genomics. You can see deeply into the workings of a microorganism before you, or even a human cell. I took that and actually helped create Human Genome Sciences, where I thought if we could do it for the few genes of HIV, we could do it for all the genes. And in fact, it turned out to work. That's a basis of much of modern medicine. So you get the genome sequence and you can use it as a drug target, or you can use it to make new vaccines. And you take pieces of those genes, you put them into adenoviruses, or you make messenger RNAs, or you use older techniques and you grow up the virus and kill it. All of that is going on. Or you take a piece of the virus and you make a protein, and that's a vaccine candidate. All of that happened. But it happened really fast because the Chinese recognized the nature of the disease, shared the information of the sequence. That was widely disseminated. And it also happened because we were primed to respond. SARS and MERS, the two previous coronavirus lethal infections, gave us all the tools we needed, because there was a whole group of scientists that already tried adenovirus vectors against MERS and SARS. They'd already tried protein vectors. They'd already tried killed vaccines. They hadn't tried the mRNA, but they were certainly primed because they tried Ebola. So we had a whole community just ready to jump. In addition, in the United States, we had the whole legal process worked out to make sure this thing went through like grease lightning. And that was a process we put in place in 2001, 2, and 3, called BioShield and BARDA, to allow us to do rapid response with vaccines and drugs for new diseases. And I helped craft that language with the National Institutes of Health, where the language we put in was first just going to be bioterror threats. We said, no, we have to make sure it's both man-made and natural origin. new biological threats of man-made and natural origin. And by putting natural origin in, we had all the legal authority to move forward lickety-split. And that's what happened. And we were using it. So we were institutionally prepared, we were scientifically prepared, and it took that spark of having the information from China that let us get going quickly.
Can you go into a little more detail about the scientific collaboration involved in reaching all of these solutions and the need for that continued collaboration? And then also talk to us about the wider potential of, I guess, a system of collaboration which has been set up.
Right, well, we're not done with the pandemic, or let me put it another way, the pandemic is not done with us. As the rates of infection come down in Europe and the United States, they're rising sharply in South America, in Africa, and we've just seen an enormous human tragedy in India, which is now spreading to Southeast Asia. And even countries which had contained the pandemic by public health measures alone are subject to continual assaults. And as I speak, there are several cities shut down throughout Asia. Melbourne, the state of Victoria, the whole of Taiwan, and about 100 million people plus in southern China are under restrictions because the viruses seep back in. And what's happening is the virus is evolving to become more and more transmissible. We've seen it go stepwise from, let's say, a rate of transmissibility of 1 to 2 to 4, now 6, and possibly now 8. That means a little bit of virus, you've got infected. And instead of infecting just one person, it can infect many more people. And so we've seen countries like Brazil has had one terrible epidemic where most people got infected in certain parts, get reinfected. The same thing in India. So this is not over. We need every bit of knowledge and cooperation. So you asked me for some specific details. You know, when you look at how these viruses are becoming more and more transmissible, there is a group of people that I am in real touch with, I would say through the literature on a daily basis. I start off every morning and every evening looking at the literature, and there are jewels and gems every single day. Let me just give you an example of one. This virus is sneaky. It gets in and it quiets your immune system for long enough to get out. That's its basic trick. You don't feel sick. When you get infected with a virus, it's not the virus that makes you feel sick. It's your immune reaction to the virus, just like a vaccine. That's why when you've got the vaccine, some people feel like they've got the flu. It's the same thing. So this virus can shut down the immune system long enough for it to get out again. And then you start feeling sick. Well, how is it doing all that? And what's it doing? Well, a lot of collaboration between people working in cancer and cancer biology, people working in virology, have figured out that maybe it's shutting down interferons, but maybe if we stimulated, something happens a little later down the pathway, we'll be able to short circuit what the virus is trying to do, prepare us and prevent the virus from getting a foothold. That's a good idea. Well, people have thought of that for cancer. So can we get the rev up the immune system a little bit better? And so a drug that was being used for cancer and published for that, people thought, oh, let's try it to see if we can prevent these viruses from killing mice. And sure enough, it works. I just did a little Forbes piece on that. But that's one kind of example of how different kinds of fields come together. Deep, deep knowledge of what this virus is really doing and how it's doing it. Turning off interferons, understanding the details of that pathway, understanding what is the potential target based on 30 years of research on what's called innate immunity. And then understanding that there might be a drug from a different field that could be used for that. I mean, that's thrilling. That's exciting. It's like watching the best movie unroll every day with a really surprising and often happy ending.
It's been estimated that it will cost the world $30 billion to vaccinate everyone. Could you talk to us of ACT Accelerator's proposals in making the richer parts of the world, the richer countries, encouraging, I should say, the richer countries to contribute to the cost of vaccinating everyone?
Well, I think that's you've lowballed it. I think the cost is going to be, people now are saying 50 billion and maybe 100 billion. It really doesn't matter. That's small potatoes compared to the trillions, tens, and even higher trillions of dollars in lost productivity and in human suffering and in lost lives. So that it's a very small price to pay for the world. Now, I mentioned that even if you've protected your own country, you're still at risk. New Zealand, Australia, and even with vaccines. Let's just do a little math. Suppose you have the very best vaccine, 95% of people protected. If you have 300 million people like you have in the United States, that's hundreds of thousands of people who are not protected even by the best vaccines. You want to protect those. And you want to protect the children, which were not now protected by vaccines, which may be. And even then, as vaccine wanes, more people are going to be susceptible. And there are going to be viruses that come in that basically evolve to get around our vaccines like flu does. This really looks a lot like flu now. Maybe it'll be tamer than flu. It looks worse right now, but maybe tamer. We don't know. So you've got to have the whole world vaccinated. And is it giving them vaccines? Surely, if you can. Right now, there's a problem. There's a shortage of vaccines in many countries. We're just getting over that shortage in the United States to a place where we can ship out our best vaccines. But I actually have a different take on that, and something I've been working with groups in the development banks and the World Bank and IFC to get them moved along, which is creating the capacity to make these new generation vaccines in South America, in Africa, in the Middle East, in Southeast Asia. And it's beginning to happen, but it's happening far too slowly. We need something called special drawing rights, which allow people to draw down additional funds in emergency from the IMF. And we need the development banks to put up big funds to create the high quality manufacturing facilities for this and for many other diseases. It's something we as a world need to do, not just provide vaccines, but provide the capacity and the training so that countries can make their own vaccines, or continents can make their own vaccines for their own people.
The commercial organizations Johnson & Johnson, Pfizer, and Moderna have reported huge vaccine revenues in the first quarter of this year. What do you think they could directly do in alleviating this situation?
Well, first of all, they can donate vaccines. That's an obvious one. But, you know, there's a big discussion over patent waivers. And I've looked at that question, and I've actually worked on that question for a long time. And I have a slightly different take from many people. You know, right now, let's take hepatitis C. I wrote an article on how Egypt has wiped out hepatitis C by testing the entire country for hepatitis C and making drug treatment free. And the reason they were able to do that is they were able to get the hepatitis C drugs, which cost $80,000 to cure somebody in the US, for $45. Okay, and that's because, not because the patents were waived, but because under the TRIPS agreement, there's an exception that if you really need the drug for a national disaster, you can make and use the drug for that purpose. So that exists. And also, you know, we went through this for HIV for a long time. It was a big push. It was heavy lifting. There was kicking and screaming by a lot of the pharmaceutical companies. But eventually it was agreed that there'd be a tiered pricing strategy. In countries that can afford it, you put in enough money so that the companies can give you even more drugs in the future. But in countries that are middle income, low income, or really at the bottom, you make a sliding scale. And it isn't waiving the patents, it's making an agreement. Yeah, in a middle-income country, we'll sell an 80,000 drug for 3,000. In a low-income country, we'll sell it for 1,000. And if it's really poor, the TRIPS will kick in and they can have it for whatever cost it makes to make it. Those are the kinds of systems that are already in place. Once you deal with patent waiver, you know, patents are enshrined for a very good reason in the US Constitution. Benjamin Franklin, I think, summed it up best when he said, a patent pours the fuel of self-interest to the fire of invention. I think that really summarizes it. People get motivated by money. That's a reality. People work harder for money. And if there's a lot of money, they'll work even harder. You want that. But at the same time, I run a foundation called Access Health International. Our motto is, let's provide high quality, affordable care, accessible, affordable care to everybody in the world. That means in a lot of parts of the world, drugs at very low price that might be priced more expensively in other areas. We can do it. We should do it. We don't have to destroy the incentives of patents to do that.
What do you think can be done at a political level that is not currently being done? Maybe you can point some fingers if you would like
That's
to.
a very big question, but I would say the biggest disappointment in the whole COVID pandemic has been the socio-political responses in different countries. At the very beginning, China proved something, that socio-political action alone can contain this pandemic. They did it. Other countries did not learn from that. They called them totalitarian, they called them this, they call them all sorts of names. A few countries did. Australia did, New Zealand did, Singapore did, Taiwan did. They actually controlled it before we had vaccines there, but that didn't happen in almost all the world. It certainly didn't happen in our country. And that was a massive failure of government and the people in the country, because governments reflect what people think in the country. They don't actually lead so much as they take the direction from the people that are in their country. They do some leadership, but if the mass of the country doesn't want to do something, no leader can take them down that path. You just, no leader can do that. You just look at Biden trying to do things that Trump didn't want to do. He can't do them either, okay, because of who we are. And so that's been my major disappointment, that we as a collective body of human beings are not as responsible as we should be for one another. And that doesn't allow our governments to be as responsible for us as they might otherwise be. There's some other issues. There's structural issues, states' rights versus federal rights. But those are parochial issues for country by country. But in general, you can look at the entire continent of Europe. You can look at all of North and South America. And you can look at most, all of Africa and most of Asia, with some exceptions, the big exception being China, and see that socio-political solutions were not implemented as they could have been. And I'm not sure that any leader could have done that in these other countries, but some of the leaders were worse than others.
It would be really interesting to hear if you were given the opportunity to, let's say, sort out 3 things at the moment. What would you do, whether it is political, scientific, just to get things done? You mentioned earlier that you have this organization, philanthropic organization called Access Health International, that deals with health at a macro level. What would you do?
Well, the first thing, being a scientist naturally, I'd keep up funding and expand funding for the detection, treatment, and prevention of a whole range of infectious diseases. We do a good job, but we could do a better job. And we should do it in concert with other countries around the world. That's the first thing. And this current demonization of China is exactly the wrong way to go. You know, we don't know what happened in China. We may never know what happened in China. But what I do know is the blame China movement is destroying vital aspects of cooperation. It's 1/5 of humanity that we're essentially going to cut ourselves off from. They're going to get really angry. I know they're getting angry. And we're getting suspicious. And it's all over nothing. We don't know. And it's not going to help us control the pandemic to know that it was or wasn't a cave or a this or that. Just remember, MERS came from a cave in Africa. This is a worldwide problem. You know, one thing people don't realize is there are probably more bats than human beings on this planet. And they harbor all sorts of viruses. There are probably more birds all over the place. They harbor the flu viruses. So we have to work as a world. So that's the first thing I do. Second thing, I would change the way we handle public health in general. Public health for pandemics has to be done nationally and internationally on a cooperative basis. You can see how COVID has sort of popped and sort of hopscotched around the United States. Oh, this area is doing well. We got it under control. Pop, it's over here. Pop, it's over there. There's no uniform policy. You can see the benefit in a country like Australia of a good uniform policy. It's a big country. It's got people who are at least as independent-minded as we are, right? You know, the Australian isn't a calm human being. They're kind of a beer-drinking, active, in-your-face kind of people, yet they cooperated. Why haven't we? Why haven't probably the most similar people to Australians or Texans? Why aren't they behaving like Australians or Australians behaving like Texans? It's a really curious thing to try to work out. So I would secondly work on strengthening our entire public health systems, both within country and very good, well-supported, well-financed global efforts. And finally, there's a whole process that we in the West have been really adverse to. It's called testing, contact tracing, and isolation. That's what controls pandemics at the very beginning. If you do that right, you don't suffer. Look at the countries that did it. You can count the number of people who have died in the last year on your hands. Not by the tens and hundreds of thousands, but on your hands and maybe add a few toes. That's it. That's what we can do, but we didn't do it. So now we're counting dead in the millions, not on two hands and a few toes. That is an enormous difference. So I think that's the kind of thing we have to focus on.
The focus of this interview is how COVID-19 has changed science, and that this is hopeful. It's hopeful for science in general, but it's also hopeful for other aspects of human existence, businesses, institutions, entities, how we work together as human beings. Can you take us through how this type of collaboration could help with addressing world challenges?
Well, first thing to say is, if you're a biologist, you look at evolution. Why are we so successful as a species? And the current sort of anthropological, paleoanthropological explanation is we learned how to cooperate in hunting, in living. And, you know, when I look outside my window and I see a bird, I think, how can that bird live through the winter in New England? It does, but it doesn't have a house, doesn't have electricity. You know, how can it find its food? Well, cooperation is the essence of humanity, why we are what we are and how we live. And to the extent that we cooperate peacefully and productively, we do even better. And that's in any realm. You know, one thing that is great about science is you have a conversation with history. It's a common language that goes deep, 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 maybe 10,000 years deep. You're having conversation with minds that were figuring things out 10,000 years ago. And they're as relevant today because what they discovered hasn't changed. You know, there's all these things, and it continues. And the great thing today about the modern world is exploding everywhere. It's just accelerating. The kinds of things that took 20 years can take 2 months, can even take 2 days to move forward. So it's ever more important in any field, whether, let's say, battery storage, so we can move to carbon neutral economy. Well, that's exploding all over the place. And you could go to material science. So you don't have to use massive amounts of material to make things. Look at a Victorian factory. The cog wheels are bigger than a room. Now they're tiny little things, right? So we're learning how to use the natural world to architect things at the atomic scale, which is going to make our footprint much lighter in this world. We're learning how to make artificial meat. It's going to taste like meat. And I've even had some hamburgers, which I can say I enjoyed, which weren't ever grown on a farm. They were grown on a farm, but not through an animal. So those are the kinds of things that we can move toward. And what this experience in COVID has taught us is we're not losing by opening up and communicating more rapidly. We're gaining. Yes, there are heroes. We now recognize that obscure woman who figured out mRNA. We recognize that scientist who first put those genes into the Moderna vector. Now, I'm writing a book called Science is a Superpower. It's sort of an adaptation of my autobiography, but it's different. It goes through not just my life, but people who made a difference, the men and women who made great discoveries. And why I call it a superpower is one person can save the entire world. Look at that Chinese scientist who sequenced the virus and made it public. Look at the woman who took that sequence and put it into the Moderna vaccine. Well, those are scientists, and they're saving the entire world. Look at Jonas Salk, who changed my life. So I could go to the swimming pool when I lived in the desert in the middle of the summer before I couldn't. That's a big difference, I can tell you, as a kid. Can you go to a movie theater where it's cool? Can you go to a pool? One mind in science can change the world. And I think COVID is given the whole world a new respect for science. You know, a lot of young people were headed, especially the brightest, were headed toward financial markets, men and women both. I think that is changing somewhat, that people see the value in what they can contribute to the sum total of human knowledge to make our life better in whatever area. And what I show in my book about my own life, it doesn't mean you have to slave away in a laboratory for all of your life. You can create companies. You can hobnob with the rich and famous. You can travel the world. You can help influence world leaders to do things better for their people. You can use your passport of knowledge in many, many different ways. And I think that COVID is changing our global appreciation of the value of scientific inquiry and its values. Let me take something else. One of the biggest debates that's going around is what's a fact, right? We were sort of transiting into what appeared to be a reality that was untethered to fact. Well, COVID tells you you can't argue with nature. Nature is what it is. It's like arguing with a volcano. Am I going to get into a fight with a volcano? Am I going to get in a fight with an earthquake or a tsunami? It's the same thing as trying to say COVID doesn't exist and it's not going to kill you. It's going to do what it does. It's a force of nature. We have to realize that there are forces that affect our life, which humans can control, but can't really change their fundamental nature. They're there. We live in nature, and our best tool for making that life as pleasant as possible is science and technology, to understand what's happening around us, to prepare for what's coming and deal with what is, not what we want to be. A lot of these fact-free discussions of COVID are based on hope. They're based on desire. They're not based on reality. Albert Camus wrote a book called The Plague. And in that book, he said, in times of plague, those that define the world in terms of human values are the enemy, because they will miss the implacable enemy they face and will underestimate the force of what's bearing down upon them. And I think this has changed our relationship in a fundamental way to understanding that we live in a precarious world, and precarious in a way that can affect us, not them. It can kill your child. It can destroy your job. And I think that's a lesson that everybody should now have. And the solution to that, if you're a young person who wants to make a difference in the world, is to become a scientist. It's a great career and something that I recommend. And now it's even a better career because there's many more people to communicate with.
We've spoken a great deal about the importance of generosity and humanness and collaboration in pushing science forward. I'd be really interested to hear on a personal level who has connected with you, collaborated with you richly in order to move your human story and your scientific endeavors forward.
Well, let me begin by saying that scientists are human and we're as competitive as any top athlete, okay? We're competitive, but it's a kind of competitive where you're on a football team, and for you to do well, you have to have your other teammates do well too. So it's a co-opetition, I think is the right word. I don't want to say we're all altruistic. We're not. We're all competitive like every other human being. But within that, you can compete toward a greater good. The triumph of your team, in this case, humanity, is your team. And that's what you're all trying to do. Now, I've been extraordinarily fortunate to have mentors who have taught me some of the values of cooperation. One of my very first mentors was an undergraduate. He was looking for bright kids, and he picked me out of a class of 3,000 along with 15 others. And we spent the summer meeting Nobel Prize winners. And what does that teach you? It teaches you each one's very different, but they have a common goal. They're able to identify a really important problem that can be solved with the technologies that exist. That's a gift, to know what the problem is and to know that it could be solved. James D. Watson, as a young man, understood that technologies exist to solve a question everybody had always asked. How is it inherited? How does like beget like? Why did my kids have blue eyes? Why do they might get this disease? Why am I tall or short? Nobody had the answer, but he understood the question and the technology. Melvin Calvin was interested in how sunlight makes a tree. When I show my grandchildren a leaf or a tree, I said, this came from the air. You think there's nothing in that air? Feel how solid this tree is. You can't move it. All that stuff, with a little bit of exception that came from the roots, 90% of it came from the air. Well, how did that happen? He figured it out. Okay. When you have that kind of person helping you along your route, you have like a golden world that opens up to you. And what you realize is there's people all over the world that are interested in what you're interested in and are willing to help you, even if we compete at sometimes. Ultimately, we help each other. You know, when I was at my most competitive, I sat down and wrote a book to help people understand what the AIDS virus was. And when I did that, I came to realize the people I saw as my most fierce competitors were really serious, good-hearted minds trying to solve the same problem. Yeah, they might try to beat me, but they were doing something that was really valuable. And I understood when I read not just one of their papers, their whole train of research, how they got to where they got. And that was really important for me to understand that no matter how competitive you might be, pay attention to everybody and I would say even the honor of their intellectual integrity. That they are trying to solve the same problems you are, even if they're trying to beat you. And in the end, it's a cooperative enterprise. I think that is one of the most valuable things that I saw. And by the way, each of those Nobel Prize scientists were as competitive as an Olympic champion. They really wanted to win, but they wanted to solve important problems and help others follow and train generations of people to follow in their footsteps.
Dr. William Haseltine, thank you very much for your time. It's been an absolute pleasure. And thank you for moving the human story forward.
You're welcome. Thank you very much.
Thank you very much for being with us on this episode of the ideaXme show. Our mission is to move the human story forward by sharing knowledge of the future. You can find us across the internet on all the major audio podcasting networks at www.radioideaXme.com, YouTube and Vimeo. Please subscribe